topic called closure property and minimization of DFA through the table filling algorithm under the model 1 of automata theory and computability, that is 18CS 54. The following are the steps we need to be followed for the presentation. At the beginning, I am going to discuss the different closure property of deterministic finite automata, which belongingness of their regular languages and regular expression, followed by the minimization of deterministic finite automata concept. After studying the algorithm, that is a table filling algorithm, so once we understand the table filling algorithm, so then we are going to solve some problems. So that is with help of the table filling effort. These are the presentation milestones we are going to, I am going to follow, that is. So here, so the subsequent slide will be discuss about the closure property. So that is the first property is that is a regularness. On the other hand, certain operations on regular languages are guaranteed to produce the regular language. The following theorem are referred to as a closure property of the regular language. So it refers to some operation on a language resulting in some new language that is of type that is originally operated on the regular. So we won't be using the closure property extensively. We will see the theorem. Closure under union. Consider the L and M, all languages, and the input symbol sigma. Then this union is also language that contains all the string either in L or M. So that is a union. So further, let's consider R and S language. That R and A plus S is the union of these two regular languages. If L is equal to L of R and M is equal to L of S, then these L of R plus S is the same as L union M. That is a under union. Next, that is if sigma is a different for L and M, then sigma for L union M is so union of the alphabets for L and M, the alphabet for M. Closure under complementation. Let L and M be the language over sigma, that is set of inputs. Then L cap, that is L dash, is the complement of L, which is a set of string that is a E sigma star, that is not in L, that is sigma star, that is not in language L. In other words, complement of language is everything that is not expected by the language over our alphabet, that is sigma. Here is an argument as to why complementation is closed. To complement a language, construct a DFA for that language, complement the accepting state of the DFA. Note that this requires there is no missing transition in the DFA. All the transitions should be recorded, and if the automation dies on missing edges, these states will be missing from the complemented DFA, which should be accepting states, right? So that's why no edges will be leave or discouraged, right? So closure under intersection. So L and M will be a language over input sigma. Then L and M is the language that contains all the string that are to be both in L and M. To show the closure under intersection, note the De Morgan's law, which help us. L intersection M is equal to L union M, that is individual L cap and M cap, and combined L union M is also over cap. So that is a De Morgan's principle, which tells about more intersection. Closure under union and complementation seen, therefore we also closure under intersection. Closure under difference. L and M languages over sigma, then L minus M, the difference of L and M is the setup string that are in L, not in M, right? That is a difference that present in a L, but they are not in a M. So to show the closure that L minus M is equal to L intersection M complement. L intersection M complement is nothing but a difference, that is says the who are the element in L that is going to be listed, the elements are going to be absent who are not in M. Since seen closure under intersection complementation, we also close under a difference. Reversal. The string consider A1 to AN, and also the reverse of that is AN to A1. Reverse. We'll show that W of power of R to denote the reversal string W. Example 1011. The reverse of this is 1101. The reversal of language L written L power R is the language consists of reversal of the all strings. The reversal of regular language produces another regular language. We can show this uniformly using the automation of A. Reverse all the edges in the transition diagram for A. Start state of A be the only accepting state for the new automation. Start state become the accepting state. Create a new start state P0 with a transition on epsilon to what were the original accepting state of A. This creates a reverse automation for A that accept the strings if and only if A accept the reverse, that is W power R. Closure under concatenation, right? Closure under clean star concatenation. We have already shown this for regular expression in the construction of an equivalent epsilon NFA for the star operation. See, closure under concatenation seen already for regular expression in the construction of the equivalent epsilon NFA for concatenation in the previous discussion. The one more property called homomorphism. Closure under homomorphism. See what will the homomorphism. Given language L with alphabet sigma, that is 1, and homomorphism H is defined from the alphabet sigma 2. For symbols S, A, epsilon, sigma 1, H of A is some strings from sigma 2. That is a H of A is a some strings from sigma 2. Apply H to each symbol of a word W from L and concatenate the results in order to get the new string. So H of L is the homomorphism of every word in a L, right? L, that is a language. So every word in a L are going to be homomorph. If for example H is the homomorphism from the alphabet 0, 1, 2 to the alphabets A, B, defined by follow H of 0 is equal to A, H of 1 is equal to AB, H of 2 is equal to BA, right? So with this definition, find the H of 0, 1, 0, 0, 1, 2, 0. Find the H of 0, 1, 2, 0. So then you can split them H of 0, 1, 0 into H of 0 union of H of 1 union of H of 2 union of H of 0. If so, so here the A will be from H of 0. So this is H of 0. And AB will be H of 1, AB will be H of 1, and that is H of 2 is a BA, H of 2 is a BA, H of 0 is what? A. So the four terms are A, AB, BA, A. We obtained the homomorphism of 0, 1, 2, 0. Right? So to take one more example, H up 21120, right? H up 2 is a BA, H up 1 is a AB, H up 1 is a AB, H up 2 is a BA, H up 0 is a A, right? So I hope from these two example we are able to understand. So let me make some more a little complex. Instead of giving direct the numbers inside the homomorphism function, we can introduce one more, that is star, that is repetition. One star is a either 0 ones or 1 ones or 2 ones or n ones, that is one star. 0 is a clean star, it is a repetition, right? So H up 0 is what? A. H up 0 is A. H up 1 star, H up 1 is a AB, right? AB whole star, AB whole star, because one whole star is there. So H up 1 after homomorphed we may obtain AB. So AB we can put it in a homomorphed, that is a enclosed by brackets and over star, because that is inherited from the 1 star. So instead of 1 star, H is a homomorphed and we obtained AB. So AB you can place in the place of 1, so that star will be inherited, right? So H up 2 is what? H up 2 is a BA, right? So these examples are able to understand the concept of, help to understand the concept of homomorphism. So let us see, in the other hand, the converse of this is the inverse, right? Converse of homomorphism. A H may be applied backward. This is denoted as a H inverse L, or the inverse of H, which results in the set of string W in sigma star, such that H of W is in L. Note that while applying the H to string, it produces the single string, get a set of strings in the reverse. So if H is from the alphabet 0, 1, 2 to the alphabet AB, defined by H of 0 is 1, H of 1 is AB, H of 2 is BA. So then go for reverse of homomorphism is a AB. What is a reverse homomorphism? Let construct the three string map under the table AB, A. So that is a H inverse of 0, 2, 2, 1, 2, 2, 1, 1, 0 and 1, 0, 2, right? So here the result of H inverse is also regular language, right? So H of A is a 0, H of A is 0, H of BA is a 2, H of BA is a 2. Similarly 0, 2, 2 for this string. H of 1, 1, 1, 0, H of A is a that is called H of AB is a 1 and AB is a 1. So H of A is 0. So other combination 1, 0, 2. So H of A is a 1, H of 1 is a AB, H of A is a 0, H of A is a 0, H of BA is a 2, H of BA is 2. So this is also reverse one, right? So after understanding this closure property, so let me proceed further. One more concept called minimization of the deterministic finite automata through the table filling algorithm, right? So to test for equivalence, need some method to minimize a DFA. So equivalence, to find the equivalence, and that will help us to minimize the resources. Resources may be number of states and edges. So by reducing these states and edges, so definitely DFA will going to be minimized, right? Which help in various aspects, either maybe computational aspects or memory related aspects, right? So we are going to be reduced to the largest extent possible. So if we are going to reduce the number of states, then it is quite interesting, and also it helps to reduce the help us to reduce the number of states in a DFA diagram, right? So here two states consider the two states P and Q are equivalent in a DFA are equivalent, right? So how they are equivalent? If this condition is satisfied, so delta cap of P comma W is an accepting state if and only if delta cap of Q comma W is an accepting state, right? So both the P and Q should be a accepting state on the string W, right? On the string W, both should be P and Q. After consuming the string W, both should able to reach the accepting state. Then we can say P and Q are equivalent. So this may be a classical definition. From this definition, we may partially able to understand the equivalent concept. So after solving some of the problem, so we may be able to concretely understand the concept. In that direction, let me proceed. If we have reached the state P or Q, then they are strings might get that will lead to an accepting state. After consuming the W, it may lead to accepting state from P will also lead to an accepting state Q, right? In other words, in a way more diluted way, that is will be concept will be understand. Also, any string W does not lead to an accepting state from P or Q. If this condition holds, then P and Q are not. If this condition, that is any string does not lead to the accepting state from P or Q, then condition holds, then P and Q are equivalent or indistinguishable, right? So those are indistinguishable or equivalent. Then if this condition is not hold, then P R and Q are distinguishable. If the condition is holds, then we can call it equivalent. If not, not equivalent. In other words, if the condition holds, we can call it indistinguishable. If the condition not holds, we will call it distinguishable. So equivalent or indistinguishable, distinguishable or not equivalent. These two terms are alternatively exercised in most of the literature, right? Similarly here, equivalent or indistinguishable, or not equivalent or distinguishable, right? So if the condition, the simplest case of the distinguishable pair is an accepting state and non-accepting state. If this case delta cap of P comma epsilon is an accepting state, but delta cap of Q comma epsilon is not accepting state, so in that case it is a distinguishable. Therefore pair of an accepting and non-accepting states are distinguishable. Pair of an accepting and accepting are indistinguishable. The pair of an accepting and non-accepting states are distinguishable. Very simple, right? So there is accepting and accepting is there, that is a equivalent or indistinguishable. If it is accepting and non-accepting, you will be there, that is a distinguishable or not equivalent, right? So after understanding this theoretical concepts, so let me see the algorithm to distinguish these pairs. The system A that has a Q0 to Qn makes a diagonal table. To exercise this table filling algorithm, and consider that the state diagram consists of Q0 to Qn. Make a diagonal table out of it with a label 1 to n on the rows. 0 to n nodes are there in a state diagram. Then construct a table. In that table the number of rows are 1 to n. Clear? And what are the columns? 0 to n minus 1 are the columns. 1 to n is a rows if 0 to n states are there in a diagram, and 0 to n minus 1 are the column to exercise this algorithm. So initialize the table by placing x in placing x for each pair that is a indistinguishable. So distinguishable, that is a accepting state, right? So accepting state, initially this is a pair of an accepting and non-accepting states initially, where the final state is there. So in this row and corresponding column place the x, in other words, right? So initially this is an any pair and accepting and non-accepting states. Let p and q states such that for some input symbol a, that is r is equal to delta of p comma a, and s is equal to delta of q comma a, right? So the pair r and s is known to be distinguishable, right? So they have x in their table entry, then the pair p and q are also distinguishable. So place x for pq in that table. So that distinguishable we can have. Repeat the step 3 until all pairs have been examined, right? So the repeat the step 3 and 4 again for any empty entry in the table. If new x can place, then the process is complete. Any entries in the table without x mark are pairs of the state that are equivalent, right? So the pairs, the x present in the box which represents the pairs is distinguishable, and where the cells do not have x, do not receive the x, then the such pair you can call as equivalent, right? So equivalent. So if equivalent and non-equivalent, they form their separate group, right? So this equivalent will not never join with the not equivalent, or distinguishable never join with the indistinguishable, and vice versa, right? They will form their own separate group. In that direction, let we see some problems after thoroughly understanding the concept of the table filling algorithm philosophy. So that concepts which help us to understand or solve the problem in the subsequent slide. Once these equivalent states have been identified, they can be joined into a one state to make a new state. Minimized automation DFA have unique minimum table minimum state equivalents, right? So in that direction, let we see the example. The simple example we considered here. So in this example, there are three states are involved. Those are P, Q, R. Q and R are the final state, and P is the initial state. According to the nomenclature of the nomenclature or dimension of the finite automata, that is a m is equal to we have studied, that is pi tuples, that is a q number of states, that is pqr, and sigma, that is a input 0 and 1, and delta, that is a q into sigma. So those are the transitions, and initial state is a p, and final state is a set, that is q and r. So these pi tuples, we can, from those pi tuples we can understand this diagram. This is produced for the particular problem. So having understood this given problem, so we can generate the exercise the table filling algorithm by creating a table, that is a table. So what is the rows here? Rows are 0 to n minus 1, 0 to n minus 1, that is q and r. What are the columns? 1 to n minus 1, sorry, 1 to n minus 1, correct, 1 to n minus 1, this is 0 to n, 0 to n minus 1. So this is a 1 to n, 1 to n. So pq. So after drafting this table, now it is a time to put a x mark in the cell which are distinguishable, right? Where we can put the x mark? So one possibility we can consider q and r the final states. Since q and r final states, those q and r, those q and r the final states. So those column, those column rows, we can put it as a x mark. The x is known as a distinguishable state, and we have, so that consider that how examine, that is from this table delta or epsilon, this is the transitions and this is the inputs, right? So delta of qr, that is a, this is a cell, right? So qr, that is a qr. So here x mark will be there, x mark will be there, so x mark will be there. So we have QR cell we need to be compute. So QR cell I am taken here, delta of QR comma 0 comma 1, right? At the beginning consider delta of Q comma 0. This is a Q, delta of Q, and input is a 0. After consuming the input from the current state Q2, it will go to the next state P, right? From this diagram we can understand Q comma 0, Q comma 0, it go to P, right? So that is same thing you recorded here. And similarly delta of R comma 0, delta of R comma 0, R comma 0 is also P, right? Here delta of R comma 0, initial state is R, after consuming the input called 0 and it go to the next state is P, so that is recorded here. Similarly delta of QR comma 1 is RQ, right? RQ. So this is a cell, it is a not equivalent or indistinguishable cell. So QR is a distinguishable on 0 both to P, right? On 0 both to P, not distinguishable. On 1 it is QR to QR. On 1 it go to the QR. So no X possible to place here. So leave alone. This cell will be not possible to combine with anybody. This cell will provide any evidences or witness to form a separate cell called QR. In other words, the resource Q and R going to be joined and form a single group. We'll never distinguish Q and R, its equivalent. So let's consider that. So this is the same table as reproduced here. So from the first iteration, now it is a final iteration. So final iteration, only one cell we need to be look after. So by all previous circuits we made, it is not possible to emerge further. So even after final iteration also it remains the same, that is a Q and R. So those we are going to be combined. So this Q and R going to be combined and form a one state. So that is a call the final DFA. Start from P and go to the QR after merging them, and we have that 0 will go to the P and 1 will be remain in the same state. So that will be help us to make understand the complete the concept of the table filling algorithm with a simple example. So let me take one more example with a little complex. So here instead of the previous was the 3 states, now is a 5 states. So those states are A, B, C, D, E, right? So inputs are 0, 1, right? So you can exercise the 5 tuple over this, then we'll be able to understand the definition of this what is a DFA, right? So that is a Q comma delta comma sigma comma initial state and final state, right? So after understanding all those, we are familiar with those concepts. So and exercise the table filling algorithm. So we can create, that is a column, rows are A, B, C, D are there. A, B, C, D are the B, C, D are the rows and A, B, C, D are the columns, right? So that is a 0 to n minus 1 and 1 to n minus 1, 1 to n. So 0 to n minus 1 and 1 to n, right? So A, B, C, D columns are there. So we have put the foundation, lay down the foundation to collect the information of this resource, whose are the number of states and this one. So let we begin with the first iteration. The first iteration cell tells about the consider the final state and put a X mark in all rows, right? All columns. Put a X marks in all columns. Wherever E is the final state, no? According to this diagram. So from this evidence, put a X marks into this, and those are going to be make a indistinguishable pairs, right? So next go for the second iteration. For that we can see that so you can list this, right? So vacant cells are AB, vacant cells are AC, AD, and vacant cells are BC, BD and CD, right? So these cells we need to be taken into account and exercise that transition. After exercising we will get a new pairs. Then those pairs we have to subject it to test, whether they are already marked or not. If it is a mark, then collect that evidence and corresponding input, that is a delta transition pairs we need to be considered for also X mark, right? So maybe we can let we understand thoroughly, that is by one in the step way. The delta of AB comma 0 comma 1. So I will simplify that. Delta of A comma 0. So this is delta of A comma 0 union with the delta of B comma 0. So in that I will take it out only part delta of A comma 0, right? So delta of A comma 0 is equal to what? Delta of A comma 0 is equal to what? B, right? From this diagram. So delta of A comma 0 equal to what? B, right? Similarly, delta of B comma 0 we have to compute, right? So delta of B comma 0 is what? C. Delta of B comma 0 is what? C. Delta of A comma 0 is B. Delta of B comma 0 is C. So together delta of AB comma 0 together delta of AB comma 0 is BC, right? So that we recorded here. Then we consider delta of B comma 0 as I told. So delta of B comma 0 is equal to what? C. That is C recorded. So altogether delta of AB comma 0 is a BC, right? So next we can have, that is a delta of A is equal to delta of A comma 1 is equal to D. Delta of A comma 1 is equal to D, right? So delta of B comma 1 is equal to E, right? Delta of B comma 1 is E. So we consider BC and DE. So BC and DE in this table. So who are those marked? Only BC is not marked. DE is marked, right? So since DE is marked, AB should also marked. Since DE is already marked, due to this DE witness, either BC or DE marked, then it is enough evidence to mark AB also. So we need to be mark AB, right? Similarly, let we collect delta of A comma AC. What is that TC? This is, right? This is AC. AC we are taken, that is delta of A is a B and delta of C is a B, and all together that is delta of AC comma 0 is a BB. Delta of AC comma 1 is a DE, right? So since D is marked, then AC also marked. We need to be marked, that is AC, right? So similarly, delta AD, right? This cell, this cell, no? So delta of AD is equal to AD of delta of AD comma 0 is what? BC. Delta of AD comma 1 is DE, right? Since DE marked, then AD also supposed to be marked, right? So similarly, so BC, right? What is this? This is BC, right? BC of delta of BC comma 0 is CB. Delta of BC comma 1 is DE, right? So neither CB nor E unmarked here, right? So since this is unmarked, then BC not possible to mark it. So not necessary, not eligible to get a mark, right? So BC not eligible to get a mark, right? So note it down. That is, so delta BD comma CC, 0 is a CC, delta BD comma 1 is EE, right? So this completes, that is all those. So we can put a X mark in that. The X mark, that is, we have BC got due to the DE, right? Sorry, AB got due to the DE, AC got due to the DE, and AD got due to the DE, right? So no other that BC and BC, BD and CD so are not eligible to get a X mark. So we can subject it to the further injected to this table filling algorithm. Even that will not able to get it the X marks. In other words, so those will not join to anybody. So they will make a separate group of them, right? If so, then D mark, that as we told so far, that is a D mark. So AC need to mark, right? So the pairs remain indistinguishable are BC, this is BC, and BD and CD, right? So these will be never joined with anybody. They will form their own group. So hence BC, BD, CD will together will call as a BCD, right? So BCD make their own one group, right? So from this diagram, there is a resource A was initially was there in a diagram, and BCD was joined them, and they form a group, and E will be remain alone because it is also it is a final and it is not involved here, so it will be form a separate group, right? So here consider that the DFA state table will be formed again, that is, so delta of 0 comma 1, that is A B C D, right? A B C D we obtained, so A is equal to 0 BCD, A is equal to 1 BCD, right? BCD is equal to 0 BCD, BCD of 1 is E, BCD delta of E comma 0 is GE, delta of E comma 1 is also E. So this is the DFA state table, right? From this state table, so which is able to understand that is Q is equal to A comma B C D comma A, and F is a final state, sigma is a 0 comma 1, and delta is a transition of Q into sigma, right? So from these two examples we are able to understand thoroughly of table filling algorithm. So in that direction, the one more effort to understand the further more concrete way, so that example 3 is given here. So this consists of how many nodes? 8 nodes. The start node is A and the accepting node is a C, which is the double circle. So we know the nomenclature of the DFA, which consists of 5 tuples. So those we can include 8 states are there, initial A and final C, and transitions are sigma into what is called that is a Q states, that is delta. Let us begin with the first iteration. So first iteration, what set is? We can say that 0 to n minus 1 nodes are we need to be put, and 1 to n nodes we can put here. 1 to n nodes are. So B C D E F G H, A B C D E F G, right? So this is a 0 to n minus 1. This is 1 to n nodes, right? N to 1 to n minus nodes are columns. 0 to n minus 1 are the rows. Consider the C is a final state. So wherever the C rows and columns are there, so there you can put the X mark, right? So C here put the X mark, right? So after putting X marks, just go to the next iteration. So that is a second iteration. So what we computed in the previous slide, similarly we can record all the cells, vacant cells like AB, AD, AE, AF, AG, AH, and BD, BE, BF, BG, BH, and compute DE, DF, DG, DH, and EF, EH, EG, EH, and FG, and GH. So these cells we have to record it, and those we need to be compute and find the putting of X marks. So there according to them we put the X marks. Even then there are some cells are empty. This is AG and AE and BH and TF. These cells are still remaining vacant, and go to the final iteration. In the final iteration, AG has received new computation, and even after final iteration, the cells called AE, BH, and DF are still remaining are empty, and so those cells we can make it consider. So state BH, AE, and DF are equivalent because they are forming their own separate group, right? So they are not able to or interested to join with any other group, so they will form a separate group. So those are indistinguishable. So if so, so that indistinguishable we can form a separate group, and those tables, state table will be there, and corresponding the state diagram will be able to produce. So we have seen in the initially that was the 8 states were there. Now it got reduced into drastically got reduced into 5 states and also edges. So that is a maximum number of resources going to be reduced here and saved here, right? So that is a effort of the table filling algorithm, which help us to reduce the maximum resource in the table, right? So we have seen some examples, and after definition, do you think it is possible to have some other equivalent DFA algorithm as does in DFA currently solve the problem? Further reduce into few state, it is never possible. right? So the table filling algorithm is a maximum effort, so no alternative. That is, if such a DFA existed, then minimization process would be find a non-distinguishable states, right? So I hope from this lecture you are able to understand the concept of closure property and table filling algorithm concept. So that table filling algorithm, we have spent more time on this. We solved some examples. From this example, I hope you are able to follow the concept and you are able to solve. So if you have any queries, you please post to this query to the mail ID bhajan3nu@gmail.com. Thank you for patient listening.